how far can we go? So in this video, let us see like how far can we raise the ends of the RFC function and solve it. Yeah. So before we begin, let me give you the idea of what complementary error function is. So basically, it's related to the Gaussian integral. This integral over here. This integral is equal to root pi by 2. Yeah. Now, like if it's not infinity but some other number x, then in that case, okay. So basically, let me not write x again. Let me write it over t dt. Okay. So if this integral is going from 0 to x, or let me do it like this. Let me do it from 0 to let's say n e to the power minus x squared dx. Okay, fine. If it's going up to n, now this integral over here is root pi by 2, but it's slightly less than root pi by 2, and that thing will be captured in this function orf of n. Okay, so this orf of n will go from 0 to infinity. Yeah, sorry, from 0 to 1. If n is infinity, orf of infinity is just 1, value will be root pi by 2. If it's 0, orf of 0 is just 0. So that's why this orf acts as the error function for the answer with respect to root pi by 2. Yeah. Now, if this is from n to infinity, this is just complementary to the earlier function. Yeah. So this is known as a complementary error function, and this is root pi by 2 times complementary error function. Okay. So now using this definition, we can also define complementary error function of n as 2 by root pi in this integral. Yeah. Now if we have to, let's say, differentiate RFC of n with respect to n, we might need that. What we can do is we can write the constant as it is. Yeah. And basically, so let's say the integral of this function is, let's say, it's a of x. Yeah. And now we will have a of infinity minus a of n. Okay. So now when we differentiate, this will be 0 minus, and it's, if we differentiate this, we will again get this e to the power minus x square function, but at n, it minus e to the power n square. Yeah. That's why its derivative will be minus e to the power minus n square. This will be helpful while solving the problems. That's why I did this. So now you have the introduction part, and we can now start solving the problems. Yeah. Let's move on to the problems now. So for the first function, let us see how we do that. We can basically use the integration by parts. Yeah. And if we use integration by parts, first of all, the function will be as it is, and then we will have x over here as the integral of 1 minus integral from 0 to infinity. Now the derivative of this function is 2 by root pi times minus e to the power minus x square. Yeah, I derived it earlier. Yeah. And then integral of 1 is just x dx. Okay. Now this minus minus will be plus, and this is from 0 to infinity. Now I told you, now you can see from this thing, this definition, that if n is infinity, orf of infinity will just be 0 because the limits are same. And if it's 0, then 2 by root pi into root pi by 2, that's 1. So you need to know these two values, that orf c of infinity is 0 and orf c of 0 is 1. Yeah, that's why at infinity orf c is 0. So 0 times, okay, just 0 times infinity, and then you need to use limit. Yeah, so if you use limit and then use L'Hopital, you will notice that this is in fact 0. And over here this is 1, this is 0, so minus 0 again, and plus 1 by root pi integral from 0 to infinity of e to the power minus x square and then 2x dx. Okay, so 1 by root pi. Now if we let x square as y, 2x dx will just be dy. So that's why we will have e to the power minus x square by minus 1 from 0 to infinity. Now at infinity, this thing over here will be 0, minus at 0 this will be minus 1. So our answer is 1 by root pi. Okay, so we solve the first one, and this is 1 by root pi. Now let's go to the second integral, of c square of x dx. Okay, so we have integral from 0 to infinity of orf c whole square of x dx. Again, let us choose the integration by parts, and that gives us complementary error function of x, and then x from 0 to infinity minus integral from 0 to infinity of 2 times complementary error function of x, and then minus 2 by root pi e to the power minus x square. Yeah, so that's the derivative. And now we will have a x dx over here. Integral of 1 is x. Now this is from integration by parts, and now at infinity this will be 0 times infinity, but we use limits and get 0. Also over here also 1 times 0, that's also 0. And here minus minus will be plus again, plus. Now we can take 2 by root pi outside. Integral from 0 to infinity, we have orf c of x. Yeah, and over here we have e to the power minus x square times 2x dx. Yeah, so e to the power minus x square 2x dx, and then orf c of x. Yeah, so we have these items. And now we can again use integration by parts, as this as b and this as u. So we have 2 by root pi orf c of x, and this thing over here will just be e to the power minus x square by minus 1 minus integral from 0 to infinity, and this is integral is 2 by root pi times e to the power minus x square, minus over here as well, and this over here is e to the power minus x square, sorry, minus x square by minus 1 dx. Yeah, and now let us go to this side. Yeah, after there. Okay, so what do we have now? This is to add from 0 to infinity. Yeah, and we can notice that minus minus also cancel each other out. So we have 2 by root pi. Now orf c of infinity is 0, so this will be 0. Yeah, and also e to the power minus infinity also 0, and then minus orf c of 0 is 1, this is also 1, and minus 1, so minus 1 minus 2 by root pi times integral from 0 to infinity of, this is e to the power minus 2x square, e to the power minus 2x square dx. Okay, so now this is plus 1, so we have 2 by root pi minus 4 by pi. And now what do you think about this? You can easily integrate this function. Yeah, basically per minus ax square, this is just root pi by 2, sorry, 1 by 2 times root pi by a. Yeah, so this is 1 by 2 times root pi by 2. For a, this is the normal function, normal definition. So we now have 2 by root pi minus root 2 by pi, root pi. Yeah, is it? Yeah, okay. So now we have the answer 2 minus root 2 by root pi, and that is the correct answer. Yeah, let me write that over here. Okay, wait. Okay, 2 minus root 2 by root pi, that is 2 minus root 2 by root pi. Now let's go to third problem, or c cube of x. Now this is gonna be a lot interesting because this is kind of a bit more complex. The complexity is increasing. Cube of x dx. So let's go with the same approach of integration by parts. Or c cube of x and then x from 0 to infinity minus integral from 0 to infinity 3 times orb c square of x, uh, 2 by root pi minus e to the power minus x square x dx. Now this is just 0 minus 0, we all know that, and this minus sign comes out, we all know that. Integral from 0 to infinity, now this is 3 by root pi and then orb c square x, yeah, and then e to the power minus x square 2x dx, e to the power minus x square 2x dx. Okay, and yeah, 3 by root pi or 3 square x, yeah. Now again let us use integration by parts. So this will be 3 by root pi. Here we will have orb c square x e to the power minus x square by minus 1 from 0 to infinity minus integral from 0 to infinity. If we differentiate this, we will have 2 times orb c of x, and this will be e to the power minus x square by minus 1 dx. Okay, so now we have 3 by root pi. At infinity this is 0, this is 0, minus at 0 this is 1, this is also 1, so minus 1, minus this is 2 times integral from 0 to infinity of orb cx, and since there's minus it will be plus, yeah, e to the power minus x square dx. Okay, so now we can write this as 3 by root pi plus 6 by root pi times integral from 0 to infinity of orb cx e to the power minus x square dx. And let me check if there's any mistake in the signs. Basically we had minus sign, yeah, that's fine, and now this is oh, I think I missed something. Here when I differentiated orb c of x, here I should have also included uh, 2 by root pi. Yeah, so let me erase these things. There's already a mistake. I did feel like I have made one. Okay, so we basically need to have 2 by root pi times minus e to the power minus x square times e to the power minus x square by minus 1 dx, and the minus minus now cancel out, so this minus sign over here will be minus again, no change in the sign, so minus minus, and over here we have 4 by root pi. Now over here we have 4 by root pi, and then this will also change, so this will now be 4 by root pi, that will be 12 by pi, yeah, and now this will be e to the power minus 2x square dx. Now that will be e to the power minus 2x square root of x. Now over here, like if you try to use integration by parts, that will be a lot messier than what it is now. So a good way will be to change this to a double integral. Yeah, 0 to infinity. Now we know that RC of x is just integral from x to infinity of e to the power minus t squared dt. Yeah, yeah. So we can change it to integral and then exchange the order of integrals, and that will simplify our task. Yeah, minus 2x squared dx. Now we can still what we can do is we can let y equals to t by x. Yeah, and that will help us take the integrals from 1 to infinity. If we do y equals to t by x, if we do, let me write it over here. If we do y equals to t by x, that will change limits from 1 to infinity, and now uh, t will be xy. So that will be x square y square, and dt will be x dy. Dt will be x dy. Now this is a nicer one, and now this can be simplified after we'll change the limits of integral. Sorry, order of integral. 3 by root pi minus 12 by pi. Let us say it goes from 1 to infinity and then from 0 to infinity. We will have e to the power minus x square y square minus 2x square times x dx dy. Yeah, now we have changed dx dy. Now we can write this as 3 by root pi, let's say minus 6 by pi, to integral from 1 to infinity, integral from 0 to infinity. Now take minus x square common, we will have y square plus 2 and then 2x dx over here and then dy. Okay, so now if x square be g, here we will have just dg. Yeah, so that's why now it's easily integrable. It's a simple function now. 3 by root pi minus 6 by pi, integral from 1 to infinity. It is just e to the power minus x square y square plus 2 by minus y square plus 2 from 0 to infinity of dy. Okay, so now we have 3 by root pi minus 6 by pi, integral from 1 to infinity. If I evaluate this at infinity, it is just 0, minus at 0 this is 1 by minus y square plus 2 dy. Now minus minus will be plus, and we have 3 by root pi minus 6 by pi 1 by root 2 tan inverse y by root 2. Is it? Yeah, and this goes from 1 to infinity. So we have 3 by root pi minus 6 by pi root 2. At infinity this is pi by 2. Yeah, and at 1 this is minus tan inverse 1 by root 2, and that should be the answer. Now tan inverse 1 by root 2 is just cot inverse root 2. Yeah, cot inverse root 2. Again, pi by 2 minus cot inverse root 2 is just tan inverse root 2 again. So tan inverse root 2. But it feels like I'm missing something over here. I'm missing a 2 by root pi. How come I missed that? How come I miss a 2 by root pi? Oh, over here. Okay, so over here, like while I was writing the integral representation, I should also have written the 2 by root pi over here. I'm extremely sorry for that, like you had to go through all of this now. And now this is 24 by pi to the power 3 by 2 into 2 by root pi. I'm extremely sorry for this actually. Yeah. And this into 2 pi to the power 3 by 2 into 2 pi to the power 3 by 2 into 2 pi to the power 3 by 2, and then into 2 pi to the power 3 by 2 into 2 pi to the power 3 by 2. Now this will be 3 by root pi minus 6 root 2 by pi to the power 3 by 2 tan inverse root 2. So that is the answer, 3 by root pi minus 6 root 2 by pi to the power 3 by 2 tan inverse root 2. Yeah. And yeah, so we solved this as well, though I did make a error over here. I'm sorry for that. And now this was our solution, RC of x, RC square of x, RC cube of x in the definition. Over here we just need to integration by parts in this one as well, in this one as well. Over here we need to make double integral, and then we solved it. So hope you enjoyed the video, and like I also want you to try for 4th power, 5th power, and up to nth power, and generalize this per nth power. And let me know in the comment section like what's your progress. Thanks for watching. Look forward to seeing you in the upcoming videos too.